Hey guys, welcome back. This is a very important video. This takes a look at an aspect of networking called NAT, Network Address Translation, which is essential to the way the internet works in today's day and age. In this particular video, we're going to take a look at what NAT is all about. It is going to be a little review because we did talk about that in the video about private addresses and how they're used internally on the network. We'll take a look at the different type of NATs that you have. We'll actually go in and discuss the way the different NATs work, like dynamic NAT versus static NAT, dynamic PAT versus static PAT, how they actually work. But before we get started with that, let's understand why do I need NAT and what does NAT bring to the table. And again, this is something that comes from that earlier video, which was about private addresses. What is NAT and why is it that important? Initially, when the internet came about, on the internet, the addresses were governed by an entity known as IANA, Internet Assigned Numbers Authority. This is the entity that actually governs all the IP address assignments. What the IANA does, it assigns IP addresses to different ISPs around the world. Okay? ISPs in turn will assign the addresses either to enterprises, companies, a bigger pool of addresses, or to end users or home users. In order to communicate on the internet, because you need to have a unique address, it needs to follow this pattern where everything is controlled by IANA. IANA assigns it to the ISP. ISP then makes sure it assigns unique addresses to different enterprises or to end users. The IANA makes sure that it assigns different addresses to different ISPs, making sure the address assignment is unique. The problem with this type of setup is that with the explosion of the internet, which nobody expected initially, the number of public addresses that are available to be assigned to different devices is getting depleted. So IANA had to come up with a scheme that allowed them the ability to keep on using the public addresses as the internet grew. And that's where they came up with a certain range of addresses, which we have discussed in the past, called the private address range or private addresses. This was defined in a document for the standards called the RFC 1918. What IANA did was they reserved certain addresses that could not be used on the internet that were to be used on the internal network for internal communications. But when they went to the internet, those addresses could not be used. Those addresses in the class A range is the 10 address /8, a single network. In B, there's 16 different networks, 172.16.00/16 through 172.31. So there's 16 different private addresses that are reserved for private on class B. And on class C, there's 256, which start with 192.168.00/24 all the way to 192.168.255.0/24. These are the reserved private addresses. Okay? These are assigned to your internal network. This is used if one segment in the corporate wants to talk to another segment on the corporate for networking, that you can use these private RFC 1918 addresses. But when they want to go to the internet, they cannot use that address range. What they did was, what IANA did was use this technique called NAT, stands for Network Address Translation. The purpose of NAT was to take the private address and translate to a public address when going out. So you still need public addresses for these devices to go out. But what they did was, rather than assigning, let's say this company had 500 hosts broken down into two segments, rather than assigning them a full range of two class C addresses, what the ISP would do is they would say, okay, how many simultaneous connections do you need? They would say, let's say I need 200 simultaneous connections. The ISP would assign them, let's say, a single class C address. So let's say this address 192.1.20.0 single Class C address has been assigned to them. What they would do is they would create a pool of addresses on router 1 and do this functionality called NAT that would take addresses from the 192.168.10 network and the 20 network, and when they're trying to go out, change the address, the source address of the packet going out, to one of the addresses in the pool. So for example, let's say this device over here, PC1, if you guys remember from the previous video, the IP address assigned to this PC is 101. When he wants to go out, the packet, let's say to router 3, the packet would look like this: 192.168.101, sorry, 10.101, destined to 192.1.30.3, which is the public address of R3. When router 1 would receive the packet, because router 1 was the default gateway for PC1, router 1 would be set up with NAT, in which it would say if anybody comes in from either the 192.168, let's say 10 network, or 192.168.20 network, I want them to be translated to a pool of, let's say, 192.1.20.51 through 192.1.20. Let's say 250, roughly around 200 addresses that were set aside to be used on the public side. So when this device came in, it would hit router 1, it would say, hey, listen, the source address is 192.168.10 dot something. I want to translate that to one of the addresses in the pool. So it would pick an address from the pool. It would translate or change the address over here to the address from the pool. Let's pick 192.1.20.51 as the source. But at the same time, on R1, it would create what would be known as a translation table, where it would keep track of, I have changed 192.168.10.101 to an address of 192.1.20.51. So when the return packet comes in, it would know what to do with it. So this is the frame, this is the packet that would be sent across from R1 to the internet to R3. R3 would receive it. R3 will respond back and it says what used to be the source now becomes the destination. What used to be the destination now becomes the source. So he in turn is sending the packet back to 192.1.20.51. Flip the source and destination. The packet goes back to the ISP. ISP would send it back to R1. R1 would receive the packet. It would check the translation table, says, oh, I've translated 192.1.20.51 to from 192.168.10.101. So what it would do with the packet on the way back, it would retranslate or untranslate this destination back to what? Its original destination, which would look like 192.168.10.101 by consulting the translation table. Now once that's done, the packet is back. Technically, this address is still assigned to this particular outside, this translation is still there, but at the same time you have the ability to control the timeout. I have the ability to, let's say after 5 minutes, take this entry away from the translation table. That makes that 192.1.20.51 reusable for another host that wants to go out, so the other host could also use it. So I have the ability to recycle my IP addresses in such a way that a smaller range of public addresses can be used to cater to a bigger, larger network on the inside. This type of NAT was called dynamic NAT, where I have the ability to set up a pool of addresses on the outside that could be used to cater to internal addresses. The reason it was called dynamic, when I went out today, my address on the internet was 51, although my private address always is going to be 192.168.10.101. Tomorrow when I go out, maybe 20.51 is being used by somebody else. So when I go out, it will, the NAT router over here will pick the whatever the address that's available at that time, whatever's next in that pool, it'll assign me that address. So that's the reason it's called dynamic, because every time I go out, I could potentially have a different address assigned to me. And this is called NAT. This concept is called NAT, and the whole reason for doing that, you can use a smaller range of addresses on the public side to cater to a bigger address range on the inside. Every device does not need to have a statically assigned address to them on the internet. So by doing that, I'm cutting down the requirement of the number of public addresses that I need. And that's what this slide is all about. I just demonstrated to you guys what this slide is talking about. Let's take a look at it. Let's review it. IP address blocks are assigned by the ISP to the ISP by IANA. The ISP in turn will assign the IP addresses to either individual users or enterprises. When you communicate on the internet, every device needs to have a private address, so the individual users or enterprises will use these addresses to communicate to each other. These addresses that are workable on the internet are known as public addresses. Most of your addresses are public except for those ones that are defined in the RFC 1918 address range, which I specified in the lecture a bit ago. The internet has grown beyond anyone's expectation. You guys, we are aware of that. And because of the explosion, the IP addresses are getting depleted. To counter that, we have that private address range that was assigned for internal communication within the company. But when they communicate to the internet, they still need a public address. And that's where NAT steps in. Private IP addresses, so ISP assigns dynamic addresses to clients from a pool of addresses, and the client then, when they go to the internet, will get translated to that address. Once a client comes back, it can assign that address back to the pool so it can be reused for another device. So that allows you the ability, again, to use a smaller portion of public addresses in a much more efficient way rather than wasting addresses assigned to devices that are not being used on the internet at that particular moment. All right? So that's what we're going to be taking a look at over here in this particular video is how do you do that? What are the different type of NATs that you have? So when an internal user wants to communicate to a device on the internet, the private address is translated to the public address, which I demonstrated to you guys, and this process is known as NAT. Multiple internal devices can share the same public address on the internet. This allows us to conserve IP addresses. Again, this is a review from what we talked about in the private IP addressing video. Now that we understood NAT, let's go ahead and take a look at the different types and what each type brings to the table. How do I implement it? There are 4 different types of NATs that we have. We have dynamic NAT, which is an example that I gave you guys in the lecture over here, in this video over here. We also have another one called static NAT, and we'll discuss what static NAT is. Generally, whenever you do static, that means rather than having an address keep on changing, I'm going to assign an address which is stuck with that particular device. Internal device will always be translated to that. This is very important for our public servers. People on the internet that want to communicate to the company's public server or public device, they cannot have a moving target. They need to know what the address of the server is, so you cannot keep on changing it. For those devices that have an internal identity, but on the public side need to be communicated to using a public address, rather than doing it dynamically, I'll do it statically. We'll take a look at that. Dynamic PAT. In this particular example, what we'll do is we'll use a single address to map over to multiple private addresses. This is done by using a combination of IP addresses and port numbers. Okay? We'll take a look at how to do that, and static PAT again using an IP address and port number combination. We'll go into detail about each one of them as we go through it. Let's start with the first one first. That is dynamic NAT. What is dynamic NAT? That's the example that I just gave you guys. This type of NAT is used when clients on the inside initiate a connection towards a device on the internet. In this type of NAT, internal private addresses gets changed to your public address. Your public address is done, or you create a pool of public addresses over here based on the address assigned to you by your ISP. So again, to recap that example that I gave you guys, ISP has assigned this company a pool of 192.1.20.0 address. From that address, what I do is I take a pool, create a pool. Let's call it pool A. And I basically say pool A has an address range of 192.1.20.0 or 20. In my example, I use 51, so I'll stick to that. 51 through 192.1.20.0. 192.20.200. So these are my 200 or 150 addresses. That means at any given time I could potentially have 150 different addresses going out at the same time. I would define my internal addresses that can use this pool. So internal addresses that can use a pool. Let's say I want to restrict that to the 192.168.10.0 network. So anyone coming in from the 10.0 network, when they try to go out, will be translated to this pool of addresses. Once a translation takes place, R1 would create a translation table. In this translation table, it would keep the local address, which is going to be 192.168.10. Let's pick an address, let's say 105, and it'll say what I translated to when I send the packet on the internet. 192.1.20. Let's say 51. When the packet goes out from the inside we'll have a source address of 192. Actually, let me just do it on my whiteboard. I want to go through the packet by packet thing. So when the packet leaves the internal PC, it's going to have a source of 192.168, let's say 10.101, destination some address on the internet, in my example 30.3, which is router 3. The internal PC will send it to the default gateway, which is R1. R1 is also my NAT device. On the NAT device, I would have configured a pool that says 192.20. Let's say 51 to 192.20.200 can be used to cater to the entire 192.168.10 network. So when the packet hits router 1 will receive this particular packet. What router 1 will do is it will translate. It won't touch the remote device, which is 30.3, but it'll translate my device, which is this guy. It's going to translate it to 192.168. Sorry, it'll translate that to one address in the pool, any address from the pool that is available. But at the same time, it will create a translation entry over here in the translation table, which will keep track of, hey, listen, I have translated 10.101 to 192.1.20.51. So it keeps that in the translation table. This is the frame that gets forwarded to whom? On the internet. It has a source as a public address, destination is a public address as well. So now the packet is received by router 3, the destination. This is my destination device. Receives it like this. Now he needs to respond back. Source and destination will be flipped because now I'm responding back. But he's not responding back to R1, the PC's internal address. He's responding back to the public address. He does not see the PC as 192.168.10.101. He sees it as 20.51, the public address. So now the destination becomes the source. Source becomes the destination. He's going to route that packet back to R1. R1 now is going to take a look at the translation table over here, sees that 20.51 has been translated to what? This guy. I need to untranslate it, send the packet back to the PC, because the PC does not know that he got translated. He only understands himself as 192.168.10.101. So he will retranslate or untranslate the packet. In this case, 30.3 is like that. He's going to translate this guy back to using the translation table from 20.51 to the address that was the original address. And the packet would be forwarded back to the PC. If you take a look at it, I want you guys to focus on what got changed on the packet going from in to out, inside network going to the outside. The source address got changed from the internal to the public address. On the return on this, the destination gets translated to from the public to its internal address using the translation table. All right. The next time round, maybe tomorrow, when this same device 192.168.10.101 goes out, maybe this address is already being used by somebody else in the pool. So at that time, I'm going to pick another address from the pool to go out. And that's why it's called dynamic. NAT, the reason it's called NAT, if you take a look at it, the only two fields that are involved over here were the source address from in to out. So in terms of the translations, source IP changed from where? On the packet from in to out to the public address, and the destination IP. This guy changed from out to in. Got it? So either case, my address is changing from my private to my public on the in to out, and is changing from my public to my private on the back on the return packet. The return packet does the translation based on the translation table. The inbound packet checks the translation table to do it. And that's what the static NAT is all about. So over here, sorry, not static NAT, dynamic NAT is all about. As a packet tries to go from the internal network towards the internet, the NAT device will translate the internal private address to an address from the pool of public addresses configured on the NAT device. I gave you an example of that. The translation between the private public address will be stored in the translation table of the NAT device so that the return traffic can be translated back to the original and forwarded to the internal device. I showed you that as well. This entry will be created dynamically at the time the connection is made. The entry will stay in the translation table for a configurable amount of time. On a router, again, it depends on different devices. On a Cisco router, if you do it, it is too much. It's actually 24 hours. So by default on a Cisco router, this entry will stay there for 24 hours. So for the next 24 hours, this internal IP can use the same public IP to communicate to the outside. You do have the ability to change that timer, but the default is 24 hours. The internal device would not be aware that the NAT process took place because he sends a packet using his own internal internal address, which was 192.168.10.101. On the return, again, the packet would come back and get retranslated or untranslated, and the PC would receive the packet just the way it sent it out. So the PC would not be aware of it. Now, this is good for traffic going from where to where. This is for traffic going from in to out. Generally speaking, dynamic NAT is used to translate your internal addresses to the outside, but from where to where? The flow is from inside to outside. Now let's take another example over here. Let's say I have my router over here. This is my NAT device, and I have a web server down here. The web server has an IP address of 192.168.10. Let's say 25. Somebody on the internet, a PC on the internet wants to communicate to it, to 10.25, but it cannot because this is a private address. He's the one that's going to initiate the connection from where? From outside to inside. This guy needs to know an address that it can communicate to your web server, your company's web server. So what you need to do over here is you need to translate this address statically so that the PCI will not need to tell him, hey, listen, my address has changed today. You need to give a static address so that the PCs, whenever they communicate to your public servers, don't need to hit a moving target. They have a specific entry for this server. But I still need to translate it. So what I need to do over here is, because these are publicly available servers, I need to translate them in such a way that the address doesn't change. This is called static translation. In which I manually will go on to router 1 and say, hey, listen, if a packet comes in destined for 192, actually the other way around, if it comes in to 192.20. Let's say I'll set aside an address, let's say 5, it should actually go to my internal device 20.55. So I tell the PCs, hey, listen, Whenever you want to browse to my web server, make a connection to 192.1.20.5, and I set up my NAT device manually to tell it, hey, listen, any packet coming in from the outside for 192.1.20.5, it should be translated to an internal address of 192.168.20.5. So this address never changes. So people on the internet have a fixed target that your web server always has the same address, 20.5. This translation, I don't want to have the address keep on changing. I do it statically. When I do a static translation, that entry gets inputted into your translation table immediately, whereas dynamic, when the client from the inside initiates a connection, then and only then the translation entry gets created. With static, I'm creating the entry right off the bat, so any PC on the internet should be able to communicate to my web server at any given time to the configured address, which in my case is 20.5. So that's what static NAT is. Generally used for what? For giving access to your public servers so that people on the internet can access it. This type of NAT is used when internal devices require fixed address on the internet. It cannot keep on changing, like with the dynamic NAT. This is normally done when you have devices on your company's network that need to be accessed from the internet. Normally your servers, your web server, your DNS server, your email server, all these need to have fixed addresses, static addresses, so that the people on the internet can communicate to them without a problem. The configuration of the mapping from the public to the private is done on the router. Unlike dynamic NAT, this entry is created immediately. When you do dynamic NAT configuration where you create a pool and say this is my public pool and this is the range of internal addresses that can use it, the entry in the translation table is only created when the client initiates a connection. Whereas with static entries, because I want people on the internet to access me, I need that entry to be there all the time. All right, so that's a static entry. It will get it created immediately. And that's what this is. The reason for that is because the clients need to have a static target to hit. So either way, whether I did dynamic or I did static NAT, both of them, the translation was an IP to IP translation. In terms of my IP header, the only part of the header that I actually worked with was the layer 3 header. So the source and destination IP, whether it was dynamic NAT or static NAT, it was an IP to IP NAT. So I translated, let's say 192.168.10.5 to 192.1.20.5. That's the translation from an IP to IP. This is good if I want one public address to be mapped over to a single public address, private address on the inside. That means, in this case, the number of addresses that will be available on the outside and the number of simultaneous connections that I'm going to have is going to be the same. So if I have been given 254 addresses by my ISP, that means at any given time I can only have 254 internal clients or servers accessible or being able to access the internet. What if you have a larger network? Let's say you don't have 254 hosts, you have a lot more than 254 hosts. And that's where PAT steps in. What is PAT? PAT is again a flavor of NAT where it changes the IP address from private to public, but it allows you to also take into consideration the port. So it's all the reason it's called port address translation, which is a flavor or an extension of NAT, is that it not only takes the IP address into consideration, but it also takes the port number into consideration. And why is that? What I can do with PAT is I can use a single address on the outside, single public address on the outside, and map it to multiple internal addresses. How is that possible? Let's take a look at a scenario where I'm going to take the same setup over here. This diagram over here. And what I want to do is I want to use a single address. Let's say 192.1.20.11. I want this address to be used by the entire 20 network. So all the hosts on the 20 network, when they go out, they should be translated to a single address. Normally speaking, if I do that, and I take the same example over here, when the device wants to go from inside, let's say this device, PC3, tries to go out to router 3. When the packet leaves PC3, the packet looks like this: 192.168, 20. Let's say 101, destined to 192.1.30.3. It has a default gateway, goes to either router 4, router 5, which is the VIP, forwards it to whom? To router 1. Router 1 gets it. Router 1 in turn will have a NAT setup. NAT, what I'm saying is, I have a single address, 192.1.20.11, that should translate the entire 192.168.20 network. Wow, that's 254 hosts, and I have a single address going out. But what you do with this NAT is you say, I want to do NAT overload, where you want to use the same address with multiple internal devices. And how does it work? When the packet came into router 1 would change this packet. It would change the IP from 192.168.20.101 to the public address. I have a single public address, so I have no choice but to use 11. Destination didn't change. All right, so far so good. And it puts the translation table in the translation table. So my translation table right now on R1 would say I have translated 192.1.20.101 to an address of 192.1.20.11. But the problem is, if another device over here, let's say PC4, wants to go out, he's going to send a packet like this: 192.168.20.102. Let's say he's destined to 192.1.20.2, router 2. When this packet hits router 1, he is also going to change that to the same public address. And put that entry in my translation table. But that's going to be an issue, because now I have the same address mapped over to two internal addresses. How would the router 1 know when the return packet comes in whether the packet was destined for 101 or 102? Whenever a communication, a TCP UDP type of communication happens to the internet, let's say I'm going to a web server, it has two set of ports. It has a destination port, which would be the port number for the service that I'm going to communicate to. It might be port 80 for web, 53 for DNS, 23 for telnet, 25 for SMTP. So that would be the destination port in your packet. So this is your destination port. That doesn't change. So port 80, both are going to web servers, so port 80. The source port is randomly selected by the browser. Okay, some random port number. So the random port number can be anywhere from 1024 to 65,535. The PC would randomly pick that number. So what the NATing device does, it takes that number into consideration and puts it into your translation table. Some NATing devices, what they do is use that same port number to make that entry unique, because every PC will pick it dynamically. Chances are they're going to be unique addresses. So for example, unique numbers. So for example, PC1 might have picked a port number of 20,001. This guy might have picked 15,111. As long as it's in the high order port number, that's what they pick. What the NATing device does, it puts that into your translation table. It says, okay, this connection has a source port number of what? The first one, 101, this guy has a port number of 20,001. This guy has a port number of 15,111. So, and it puts it in the translation table where it puts it also in the destination packet, keeps it the same. Some of them change it, some of them keep it the same, depending on the NATing device that you go to. I'm just giving you generic NAT. So what they do is they use that information in the translation table. When this packet, actually I made a mistake over here, need to fix it. The mistake is my second device was going to 20.2. Now when the return packet comes in, when this packet is trying to come back in, this is what R3 will do with the packet. Source becomes a destination, destination becomes a source. R3 will send the packet 30.3 destined to 192.20.11, but then the port numbers will be flipped. Source port will be 80 and the destination port over here would have been, pick a bigger packet, port number over here would have been 20,001. This packet that R2 would be sending out would look similar in terms of the destination. 192.1.20.2 will be going to 192.1.20.11. Source port is 80, destination port is going to be 15111. When the return packet comes in, what the NAT device does, it sees that both addresses are coming in to 20.11. So I don't know which 20.11 they're coming into, but then it analyzes the port number. The first packet is coming to 20,001. 20,001 is the one that maps over to 101 because of the 20,001. So what it does is over here, he sees this 20,001, he sees this one as the translation to this guy. So on the return packet over here, this 20,001, because of the 20,001 would be changed back to 192.168.20.101. The second one, this guy over here, because the port number is 15111, says 15111, 20.11, I want to change 20.11, but to what address? Because 15111, it was the address over here was, this would have been 192.168, the internal address. It would change it to 192.168. .102, this guy. Okay, so it takes a look at the combination of the IP address and the port number to do the mapping. So it's not just the IP address that is taken into consideration over here, it's a port number as well. Now, how many devices can go out at the same time? It's the number of connections. I have access to roughly around 64K ports. So a lot of connections can go out using the same single IP address on the outside. That's why this type of translation is known as one to many. One address on the public side, multiple addresses on the inside. This is exactly the type of translation that takes place on your home access points that you have to connect your home to the internet, where you have multiple internal devices at your home, your smartphones, your tablets, your laptops, all of them are going out using a single public address which was assigned to your access point by your ISP, which is called dynamic PAT. All right, so now that you've seen it, let's just quickly go over the slide. Dynamic PAT, in this type of PAT, you have a client which will initiate, again, it's from in to out, will initiate the connection from inside to outside. But in this, I'm not just going to use the IP address to do the translation, I'm also going to use a combination of the IP address and your port number to make that unique entry in the translation table. Why? Because now I'm going to have a single public IP which is going to be mapped over to multiple IPs inside. The way I'm going to make it unique is using a port number and IP combination. So just to give you an example of the translation table, for all the devices going out, the public IP is going to be, in my case, the example that I gave you, all of them would have had 20.11, even if I had 3 devices. All right, internal devices, let's put them as 192.168.20.101, 192.168.20.102, and 192.168.20.103. So I have 3 different internal addresses. Outside, they're all seen as one. But how does the translation table keep them unique? By using the port numbers, the source port numbers, They keep them unique. So if this port number was, in my case, 2011 or 20,001, I'm just paying 2011, keeping a different number over here, keeping a different number over here, which are random. This entry, when the packet is received back, it'll look at that port number to do the mapping. Hence, when you do IP translation, but in conjunction with the port number, it is referred to as dynamic path. Dynamic because it's, again, going to be using a different port number for this translation entry. So the mapping is over here. So if you take a look at it, this combination of 192.1.20.11, 20.11, 20.11, the IP doesn't make it unique, but 20.11 with the port number makes it unique, that this port number maps over here, 1511 here, and 19,000 over here. So again, that's what this is. The uniqueness in the translation table is maintained by using the IP and the port number combination. NAT devices uses the client's randomly generated source port as a port number in the translation table, which can be different for different entities. So this is not always the case. In case there's already a translation with the same port number, the NAT device changes the source port number as well. So let's say I already had, let's take this as example over here. Let's say I already had 1900 used up over here, or so let's say this was not 1900. The 103 PC also happened to use this port number as 2111. So I already have 2111 that is over here. So how do I make it unique over here? The NAT device would change this port number as well. It would change the port number over here to, let's say, 19999. So it now, because to maintain this uniqueness, I cannot have 20.11 mapped to 2011, 2111, 2111. So I changed the port number as well to make it unique. So this entry is now unique from this one, but I know 1999 20.11, if I receive this packet with a port number 1999, it really is this port number and sends it to this IP. So that's what this is saying. If the port number is being used, then the NAT device will change the port number as well. Some of the devices do it anyways. Some of the NAT devices do it anyways. Some other NAT devices will use the source port number as is. Again, just like dynamic NAT, the internal device is completely unaware that the NAT process took place. So again, dynamic NAT, just like dynamic path, is for what? In to out. So internal to external, external being the internet. So both of these are based on that. Okay? And this is for dynamic NAT, which is just a one-on-one type of thing, a many-to-many, where you have a pool of addresses mapped over to a bunch of different internal addresses. Dynamic path, same concept, in to out, but it's using a single address on the outside to map to multiple internal addresses over here. Internal to external is what I want you guys to focus on. Anytime you have dynamic, it's your internal devices going to the internet. Now, just like static NAT allowed us the ability to do what? To translate my public addresses on the internet, I can do the same thing with PAT. This is where, again, I have a shortage of what? Addresses assigned to me by my ISP, because the ISP is going to charge me money for it, and I don't want to pay money. So let's say I have 3 servers over here, a web server, let's say 21, a DNS server 22, and an email server 23 on the internal network of 192.168.10.0, and I want these servers to be available on the internet. I just have a single address assigned to me, or I don't have enough addresses to give out, so I'll pick an address. Let's say 192.1.10.11. I want everyone to know this is my public web server, my DNS server, and my email server. But internally, they're different addresses. So when I have 10.20.11, I need to map it over to what? Either to 20.10.21, which is my web server. I wanted to map it over to 192.168.10.22, which is my, let's say, my DNS server. And this guy over here is 23, which is my email server. But externally, there's only a single address to do that. Again, I'm going to use a port number combination over here. I'm going to say if a packet manually, rather than letting it dynamically happen, I'm going to create a translation entry saying if a packet is received on the outside interface, which is the external interface, 20.11 for a destination port number of 80, I want that packet to be sent to my internal web server, which is 20.21, port number 80. But if the packet is received on the outside to a destination address, I'll get rid of this, of 192.20.11, same IP, but the port number is 53, forward that packet to 192.168.20.22 for port 53, my DNS server. Similarly, if I receive a packet for 192, same public IP, but the translation for port 25, forward that packet to this IP. 10. Let's say, what was it, 23. Again, this is 10 because I'm using 10 over here on the inside for port 25. So this entry will be created manually so that the servers are available on the internet. I'm using a single address to represent multiple internal servers, and the mapping, the translation will be done by looking at the port numbers. So this type of NAT is used when internal devices require a fixed address on the internet. Generally, this is when your public servers are available on the internet. They need to be accessed from the internet by clients. The only problem is I don't have enough addresses for all my internal servers, so I use a single address on the outside and map it over to what? Multiple internal servers by, again, using the IP and port combination. I'll configure this entry manually so it's available at any given time. So that's the objective of static PAT. Same thing that you did with static NAT, but it is manual. So it's, it is one to many. Single public address maps over to multiple internal servers. So this, just like static NAT, it is for what? Outside devices accessing what? Inside devices, your public facing servers. This is either static NAT or static PAT. So to recap, the 4 type of NATs that I have: dynamic, NAT, or PAT. The flow of this generally is what? Private to public. The other thing that we learned over here was static NAT or PAT. The flow is public to private, out to in. This is your public facing servers. The other thing that I also wanted you guys to take away from this particular one, NAT, IP to IP mapping only. A single IP in the translation table maps to a single IP on the inside. Whereas with PAT, it's a combination of what? IP and port number mapped over to IP and port number. The following videos, we are going to take a look at each one of those NATs one at a time. So you'll actually see them in action. You'll see a dynamic NAT, you'll see a static NAT, you'll see a dynamic PAT, and a static PAT. Each one will be its own individual video with the implementation, with the commands. Don't miss those, because those are important. Those are the places that this all ties in. When you actually see the configuration, the connections, it'll make a lot more sense. So what my objective in the next set of videos is to show you the culmination of this topology, where now we are going to set up the last portion over here, which is the connection from my internal network, which is private, 2 private networks. They should be able to access my internet. All right, we have already done the different things to set it up. We have set this up as a web server in a previous lab video. We set up this as a DNS server. We set up this as a DNS server, the ISP DNS server. We had already done DHCP. We have done the DHCP relay over here. We had done HSRP over here in this lab. We had done VRRP in this lab. So all that culminates with the 4 type of NATs that we have. We'll take a look at how to do dynamic NAT, followed by static NAT. Then we'll do dynamic PAT, followed by static PAT. So all that stuff will be demonstrated in the following videos. Do join us. I hope you guys enjoyed it. See you guys in the next video.